Good evening, students. Today we are going to find the variation of acceleration due to gravity due to depth. Before, we have to calculate the relation between the density of Earth and the gravitational constant and the acceleration due to gravity. For that, we have to consider the density of Earth material is rho, and the radius of Earth is capital R. Radius of Earth is equals to capital R. If the radius of Earth is capital R, then the volume of Earth is equals to 4/3 by R cube, and the mass of Earth M is equals to 4/3 by R cube into density of the Earth's material. Now we already know about the expression of acceleration due to gravity, that is small g is equals to gm by r square. What is capital M? Capital M is the mass of the Earth. Now putting the capital G, small g equals to g into 4/3 by r cube into rho by r square. By r square. From here we have small g is equals to 4/3 by rho g into r. That is the relation between the density of the Earth's material, gravitational constant, and the radius of the Earth and the acceleration due to gravity. Now to find the variation of acceleration due to gravity due to the depth. When an object is on the surface of the Earth, that is at the point A, small g is equals to 4/3 by rho g into r, that is at A point. Now if the object is displaced to the point B at a depth of B, then the radius of that cone reduces to r minus d. Now the acceleration due to gravity at that point B is g dashed is equals to 4/3 by rho g r minus d. Now taking the ratio of that, we have g dashed by g is equals to 4/3 by rho g into r minus d by 4/3 by rho g into r. So the variation becomes g dashed by g is equals to r minus d by r. So that is equals to 1 minus d by r. So g dash is equals to g into 1 minus d by r. Now if we represent it, the variation of the acceleration due to gravity due to altitude and depth by graphical method, let us consider OX is OX along the OX axis. We have considered the distance, and along the y-axis is the acceleration due to gravity. Here it is the capital R. AB line denotes the radius of the R, that is OA is the radius of the R, and after that it is represent the altitude. If we draw the graph, G dashed is equals to G into 1 minus d by r is the variation of the acceleration due to gravity due to depth, and for the altitude we have G dashed is equals to G into r square by r plus h whole square is the variation of the acceleration due to gravity due to the altitude from the surface of the earth, that is G dash is equals to G into r square by r plus h whole square. Now let's move to the next topic, the variation of the acceleration due to gravity of earth due to the diurnal motion of the earth. Let us consider the omega is the uniform angular velocity, and here lambda is the altitude. If this is lambda, this is the alternate angle lambda, and this is the vertically opposite angle lambda. Now if the object is placed at the point C, then there should be a centrifugal force acting on it. What is the centrifugal force? If C is equals to m v square by r. Now converting it into the omega, m r square omega square by r, we have m omega square r, because smaller is the radius of that portion OC. OC is equals to small r. Now as it is lambda, so in that direction we have FC cos of lambda, and the weight mg is acting along the CO, that is mg. Now here this diurnal motion, the weight of the object reduces due to the centrifugal force acting in the outward direction. We have mg dashed. G dashed is the acceleration due to gravity at the point C. So mg dashed is equals to mg minus of fc cos lambda. Now that is equals to mg minus fc m omega square into r cos lambda. M omega square r into cos lambda. Okay. Now here we have to convert the r smaller into the capital R, that is the radius of the r. From the figure we have capital R, OC is the capital R, and CO dashed is the small r, and that angle is lambda. Now r is the base, so small r by caps R is equals to cos lambda. Now small r is equals to capital R cos lambda. Now putting that in that equation, we have mg dashed is equals to mg minus m omega square capital R cos square lambda. Now from that, g dash is equals to g minus omega square R cos square lambda is the acceleration due to gravity at the point C due to the diurnal motion. Now let's move to solve a problem. Find the gravitational force exerted by point mass small m on the uniform rod. And what is the mass of the rod is capital M and the length of the rod is small m. This is the rod which mass is capital M and the length is small l. Now let us consider the point mass m at a distance of a. So here we have to consider a small portion of mass dm, and this is dx, and the distance of the mass m, small m, from that is x. Now the force due to the dm is df is equals to gmm by r square, where g into dm into small m by distance square is the x square, Now here that is equals to g into dm is the mass of the small portion, m by l is the mass per unit length, and dx is the length, that is dx, into small m by x square. Now here that is equals to g into capital M by a small m by l integrating dx by x square. F is equals to from a to a plus l. We will get the result. Okay students.